all these fundamentals are known, one can go into simulations, so radiative transfer calculations. And so why would you use that? It's main thing in remote sensing. Radiative transfer is used for sensor definition. So if you want to know how sensitive your detector should be, what integration times to choose, simulation is a good idea to do before. Then the calibration and cross calibration. So once one knows how much radiation reaches your sensor, sorry, then one can design your laboratory accordingly. So one can define the radiation sources and to the same level as expected in flight. Yep. Somebody else is coming in. And third thing is validation. That's what so in-flight calibration and validation. Validation is just checking if your calibration in the lab was correct. And sometimes if it was not correct and your satellite is already up, you need to recalibrate based on the ground measurements, unless you have some onboard calibration devices. And then the last thing which is often used is some sensitivity analysis. So how much are certain wavelength ranges influenced by the atmosphere? So if you have a wrong atmospheric correction, how much will it impact the results? These are why you do that sensor radiance modeling. One application which is not well, it's missing, not mentioned here, is the atmospheric correction, but that's a different story. I will go, I think, shortly into this tomorrow. Now, we already had this before. To model this situation, one has to input a few parameters into MODTRAN. So the radiative transfer code, has to know about the geometry. So locations, sensor direction, and date and time, this has to be defined well. Then one needs to know about the atmosphere. So how many gases, how many aerosols, what pressure, what temperature. The first two, being the more important ones, pressure and temperature, don't have that much of an impact. But in the beginning I mentioned the radiation source. So what's the solar spectrum in the background? And of course, what sensor do you want to simulate? So what's the wavelength range and resolution? And finally, what reflectance properties of the surface are to be input. So do I use a standard reflectance, or do I use a measured reflectance on the ground? That's the inputs you're using. And what can you get as an output? Well, you can calculate the solar flux and all these components of the radiance at the sensor or the transmittance values. So these three outputs can be generated in MODTRAN. You need to run it separately for them. So if you want to have transmittance, or if you want to have radiance, or if you want to have irradiance or solar flux. Also, if you want to get atmospheric correction parameters, is also a different kind of a run. So you have to decide first what are you up to. So, and you get a lot of outputs, and you can also define some side outputs like optical thickness, columnar amounts of gases, and so on, and atmospheric profiles to check what has been chosen internally to the code for the calculations. So these are the typical outputs. How is the calculation done? So one starts at the top of atmosphere, and MODTRAN does a forward propagation. So it goes through the layers of the atmosphere. Typically, it's about 30 layers through the atmosphere. And at each layer limit, it will calculate by statistical analysis, like the dye-sort algorithm, how much is backscattered and how much is propagated forward. So it's coming in, backscattered forward, and so on, and then it reaches the ground here. It's doing what's coming from the surroundings and how the ground interacts, and then it's propagating to the sensor. One problem is that it forgets about what it did before. So it's propagating through the atmosphere and finally has your sensor radiance, but you cannot go back. So it's not, you cannot invert easily, MODTRAN. So to invert it, you need some atmospheric correction code. So you have to simulate a few situations, and then you know which parameters correspond to one sensor radiance. That's the principle of this forward simulation. And by this can be other codes like 6S can be inverted because they summarize the whole atmosphere into one layer and with a straight path. So it's not a banded path in 6S. And if you summarize the whole atmosphere into one layer, you can invert it, but that's not done in MODTRAN. Then there are a few assumptions. First thing is that aerosol sizes have a normal distribution. This means there's one predominant aerosol size in the aerosols. So it doesn't support double peak sizes like as you would have in certain smog situations. Then it assumes the standard atmospheric composition, like in the standard models. I think this will be afterwards. And gases and aerosol decrease exponentially with height, so there are no inversion layers normally in MODTRAN. Multiple scattering is limited to about 8 streams. Well, you could increase them, but it's a matter of processing time. And usually we use inversion surfaces, but you could enter a radiative model in the background. One more thing is that MODTRAN is not sensitive to polarization. You know that aerosol scattering produces polarized radiation, and this can have quite an impact on the signal. But MODTRAN, that's a limitation of MODTRAN. The current implementation doesn't support polarization. So what do we have? Just for the RTC codes, we have MODTRAN, we have 6S, and we have LibreTran. These are the ones which we are using from time to time. There are more. There's a big list of radiative transfer codes, most of them being developed at research institutes, but many of them are not openly available or are available but in an undocumented way on a GitHub somewhere, so you don't have a validation of the codes. So that's why I'm not going into those. Then there is the HYTRAN, which is often a little bit confusing. That's not a radiative transfer code. That's just a database of extinction and coefficients or absorption coefficients of gases and aerosols. So MODTRAN uses HYTRAN database as an input. 6S also using HYTRAN, an older one. LibreTran also uses HYTRAN. All of them are using HYTRAN in the background. Ourselves, we started using LibreTran as well for some projects because of we have less limitations for licensing and so on. But it has disadvantages. It's less well validated, as MODTRAN is really one who could say the gold standard of RTC, because it has really ripened, and nobody would complain if you use it scientifically. Here are some differences between them. How many layers in MODTRAN? It's in the meantime it's 50, 32, but they're integrated into one. The amount of gases, MODTRAN has most of the gases supported because it also considers the thermal infrared. Then the HYDRAN database in the background currently is 2013. I just asked them if they will include 2020 HYDRAN, because the most recent one is 2020, but currently we get 2013. The internal resolution is the highest in MODTRAN, and we can go from 200 to 200 meters, so it's really covering the whole range of wavelengths available for standard remote sensing. Then we have this the scattering algorithms. CXS has only a 2-stream, but it can do polarization in some cases. And what is it used for? So MODTRAN is really used for spectroscopy, for all kinds of simulations. CXS is for standard satellites. Often people are using CXS. Not for calibration. Usually MODTRAN is used because you have better control. And yeah. And of course, the cost differences is relevant because the other two are open source, and MODTRAN has risen in price through the years, and I don't know what the future will be there in pricing or support. But currently, it's just as is. Questions about these codes? Okay, going further. So we have the MODTRAN itself, the blue part here, which uses some JSON inputs, some spectral albedo of the ground as files, as input files, and produces so-called tape 7 outputs, maybe solar flux. And what we built, MODTRAN itself has a graphical user interface. Currently, myself, I don't have I have almost no experience using the official user interface to MODTRAN. The reason is that the official user interface is not optimized for remote sensing applications. It's rather optimized for operating MODTRAN itself. So if you want to create simulations of non-standard situations like a horizontal path or a path through clouds or through self-defined aerosols, you should go for the original interface. If you want to do remote sensing, I rather recommend using ours. And we just repair the inputs in MODO. We can input reflectances, create these input files to MODTRAN, let run MODTRAN by itself inside, and then we analyze what's coming out from MODTRAN. We also changed the unit such that it's remote sensing units, and that's our part. We also do the convolution, so the adaptation to the sensors, it's done in MODO. MODTRAN would have an option for that, but it's less flexible there. So here you can do it through the GUI, defining the sensors and so on. It's just to show you the difference between the two packages. For MODO 6, that's how the interface will look like. We'll work with that afterwards. And yeah, I think I don't go into the details here now. We'll have for the inputs. So the old-fashioned input for people who have been worked with MODTRAN before was a very archaic tape 5 input, it's called, coming from I think punch cards, computers, and in the meantime they changed to the JSON input file, so it's human readable, and you have just a list of parameters you can set. Maybe if I'm going to that, have a look at these inputs to MODTRAN, which should be visible in here. So we have the major input. We have the definition of the atmosphere. So as mentioned before, these entities which have to be entered. We have a definition of the atmosphere, definition of the aerosols, then the geometry definition, down here, so the height of the altitudes, angles, and so on, time. Then we have the surface definition, so what is the reflectance on the ground, and then we have the definition of the sensor. And then you can define some options, what files to write, what side outputs to be written. But that's the structure of this JSON input. JSON files are quite flexible, so you can, it doesn't matter, the order of appearance doesn't matter, for instance, and you can edit them manually quite easily if you want to change certain parameters. So that's how the input is working in MODTRAN 6. Then what we did in MODTRAN, that's, I would say, for scientific use, we tried to translate this into a one big GUI, so such that you can it's all at in the same order as the JSON file. So for each block of the JSON file, we have one block in the graphical user interface, and this can be then set through pull-down menus. It looks really ugly, I know. But on the same time, you have a kind of an overview of all your settings of a MODTRAN run. This is for a single run of MODTRAN, and in the background, the full data format of MODTRAN is supported. Some of the parameters which are available in the JSON are not reflected in here, so some parameters which we consider not being important for remote sensing are not covered by this interface. But that's about the translation. That's the most complicated part. There is an easier one I will be showing afterwards or later. Some conventions which often lead to confusion. The strange thing, MODTRAN does a forward simulation from the sun to the sensor, this way around. But the definitions is given the other way around. So H1 is the height of the sensor, and H2 is the height of the ground. So it's from the sensor to the ground. It's just leads to confusion. So H1 is sensor altitude, H2 ground altitude. The angle, the sensor zenith angle, is from the sensor downwards is 180 degrees. Upwards is 0. So zenith means always 0 degrees upwards. The same applies to the sun, solar zenith angle. So that's these definitions of the angles. So the side sun angle is the angle between the trace of your observation to the trace of the sun. So this is a trace of the observation U vector, and this is the trace of the solar main vector, and this is the side sun angle. Also again from the sensor to the sun and not the other way around. These are geometric conventions. For the spectral albedo, there is a standard file in MODTRAN which you can use to enter the reflectance of the ground, but you could also enter your own reflectances, like an NV spectral library, whatever you have measured on the ground as an input to MODTRAN for the simulations. So that's also something which is done by MODO, so this interaction with spectral libraries. That's a side question. What standard remote sensing software are you using? Are you using ENVI or ERDAS or both? Or Geomatica? Wayne, maybe, yeah.
Yes, we are using both ERDAS, ENVI, and also Geomatica.
So you have all of them, okay.
Yeah.
Because in MODO we are relying on ENVI data formats, very applicable. So in all
I saw is using the IDL. Yeah,
it's an IDL package, so it's all in. So it's that's why we are also using ENVI formats. So it's in the same series, I think. Yeah. So this before I have been showing the complicated interface. This is the easier interface to do simulations. So we call this the at sensor radiance simulator. So if you know you want to have a sensor radiance, so you can enter your standard reference situation. This just tells you about the resolution and the scattering algorithm. And then you only enter the most important parameters, like how much, what aerosol model, what atmosphere model, what visibility, and then what albedo, what reflectance spectrum, and here this geometry. And then you can directly enter your sensor response. So you enter the response files, and then you create a file with the radiance at sensor from the simulation. So this is I call this the east down MODTRAN. Normally, often one makes first that, and then JSON is already stored for this situation. And when one can load this JSON file if one wants to change small things or one check what was set for further analysis. But this
Daniel, there's a question.
Yep.
For the at sensor simulator, is there any camera model that we need to select?
Yes, because of course, if you have your own sensor, we need the response functions of the sensor have to be known. So these are these band, the .rsp files. So for each spectral band, one needs the respective response with wavelength. It's an ASCII file which is well described. So you can use another one and you create one by your own, from your lab measurement or wherever from. There are some standard sensors already in the package, like Landsat or Sentinel and so on. But if you want to have your own sensor, of course, you have to provide your own information for the sensor model.
All right, thank you.
Sorry, the .rsp file is standard in MODTRAN because it's not exist in MODTRAN 4, I know, but this is a new thing in MODTRAN 6.
The atmospheric correction, you mean?
The sensor response files.
That's something from MODO. That's not in for
okay.
for MODTRAN. That's something we do.
Yeah, that's what I suspect too. Yeah, because it's not exist in the MODTRAN as I know. Yeah.
Yeah, in MODTRAN it's a little bit more complicated. Yeah, but you could do that.
Another question is, okay, I know you skip some of the option in MODTRAN because it's not applicable for remote sensing. But in the future, let's say somehow we have some other calculation that require to configure that parameter, we can manually edit in JSON. We can manually edit in JSON, and we can still run the JSON file with MODTRAN, right?
Yeah,
we without using the MODO interface kind of thing, but we are just using the MODO to produce a JSON file, and then we edit some parameter that are not included in the MODO. Then we invoke, I don't know, it's not invoke, and then I call the MODTRAN to run the JSON file, something like that.
Yeah, so it's you can run it on from the prompt directly to MODTRAN, but you can also run it. There is a small function in MODO where you can run an external JSON, and then you can still analyze the outputs with MODO and so on.
Okay.
So you can adapt the JSON and run this JSON externally, like a batch call of MODTRAN or a side call, and then you can analyze it. So that's both possible. Or you can work with MODTRAN without the MODO because it's a full MODTRAN license in the background.
Okay, right.
Both is possible.
Okay.
So for this at sensor radiance, so we have the standard configurations, and we just change this most important parameters, and then we do the MODTRAN simulation, extract the relevant parameters, and do a convolution to your sensor system, and also create the radiance unit in watts per square meter, radian nanometer, so to the SI unit. And that's how we can create this at sensor radiances and so on. So this is just how this at sensor radiances is working. We already had this as a transmittance output. maybe just a word about this so-called correlated K approach. It's something which has been already introduced in MODTRAN 5, and in MODTRAN 6, I think they further improved this to this so-called line-by-line LBL calculation. And this just solves really the problem of crosstalk between various absorptions in strong absorptions, like here you see in the strong water vapor absorptions. If you have the red line is diisode scattering plus correlated K, so that's the reference, and you had quite some difference, up to 20% with the old algorithms. So it's worthwhile to run, in short, it's worthwhile to run the correlated K approach in MODTRAN. Scientifically, it's worthwhile. Major problem is that it takes longer. So it can take a minute or two to get a correlated K approach for very high resolution. If you're working with multispectral, you can choose low resolution database, and then you won't have time issue for single runs. If creating lookup tables, like for atmospheric correction, it will still be an issue if you use correlated K. So you have to design the lookup table very carefully before running it, because in our case for MODTRAN, for EdCore, for atmospheric correction, it takes us a few days until we get a lookup table finished in MODTRAN. So we don't do this, we do this very seldomly to recreate a lookup table. But we want to have highest accuracy. That's why we use always diisode plus correlated K at high resolution. It's just a word about these options. Then another thing about what are the standard atmospheres. Here are the integral, I think that's even here, it's a little bit better. It's a little bit better here. So water vapor, ground pressure. Yeah. So it's the major difference is the water vapor amount. So it's better visible here. In kilograms per square meter for the various atmospheres, and this will impact your data significantly. In multispectral, you don't have the option to derive the water vapor from the image, so you have to provide it somehow for the simulations. And you, I guess, in Malaysia, you will be somewhere between mid-latitude summer and tropical. You can enter also amount of water vapor, which is this would be here. So you could enter it in grams per square centimeter with a little g in before, or a scaling from the model. So up here you have the atmospheric model, and you enter, for instance, 1.5, then you get 1.5 times the amount of the water vapor in the mid-latitude summer. For the gases, you also currently you should use 4 or 5, I think, ppm for CO2, but it's still increasing, unfortunately. So you have to check this out as well. But CO2 is only relevant for the shortwave infrared. For your case, it won't be relevant. But the water vapor is really relevant. It's something to adapt. Then ozone has a certain relevance. If you want to go for high accuracy, could also be scaled in the main interface, but not in the fast interface. These parameters, like pressure and temperature, don't have an influence, a visible influence in the visible. They are relevant for the thermal infrared, but here you can just choose the standard values. Here are some other gases taken from the MODTRAN manual. How much they have? It's atmospheric centimeters. It's a little bit different from this number. I think it's how they calculate the atmospheric centimeters instead of the kilograms per square meters, but I would need to check out why they get different numbers here. I just saw yesterday that they have higher numbers, but I think it's how you measure the atmospheric centimeters. I think it has to do with the pressure assumptions you take for the where you measure it. But yeah. So Then one last thing you can do with the MODO is the so-called sensitivity analysis. So one uses a tape 5 or a JSON file as an input, and then one can change only one parameter, so in a series. So if you want to know how much influence have the aerosols on your sensor signal, you take the sensor signal JSON file, and you just change the aerosol amounts, and then you get a series of sensor radiances, various aerosol amounts. That's what I mean with a sensitivity analysis. Or you take a water vapor amount and change it various times, or you take the ground altitude, and so, or you take a spectral library as a reflectance library and do a reflectance series, and then you can do such. That's the same, I think. Yeah, it's the same, and then you can do such a analysis. So here is how it's set up. You have this input tape 5 or JSON file now. It's an old view graph, and you choose what parameter you want to change or want to do a sensitivity on, and you put in the parameter series. Here it was for ground altitude in kilometers, 0, 0.5, 1, 1.5, and 2, and then you get an output. You take your sensor response again, and then it creates you an ASCII file with the series of simulations. So that's for instance, the output of that series. So you see what happens if you change the ground altitude with your sensor radiance, and the absorption of the water vapor decreases with ground altitude. That's why you get this variation in here. The aerosols remain the same because they are only the total aerosol amount has remained the same for those simulations. That's and also, for instance, comparing various sensors against each other that can be done here by choosing, but it's more for hyperspectral. I think that's not of your interest. View angle dependencies, that's something we checked out for sensitivity analysis. So if you look to the side, how much deviation do you get at certain wavelengths? Because the scattering, the path scattering is has an angular dependency because of the aerosol, the phase function. So the phase function tells you in what direction you get how much scattering. And if you analyze this, you see that this can already at 20 degrees off, you can get a significant 10% variation of the path scattering. So if you do, the clue is or the outcome is if you do in-flight calibration, you should be careful not to look too much to the side, so that's such that your analysis target should be in the center. Otherwise, you can run into such issues of scattering, or if the sun is very low, you also get in this range here where you have high variations in path scattering depending on the observation angle. Yeah, this is an adjacency simulation we did, but it's here are some. Yeah, that's I think this doesn't need to be explained now. That's just what's new, and also again to point at the differences you get for the output descriptions. I didn't put it in this presentation because now we are at a point where one has to go into the manuals and into their own simulations. So you have the user manual where you have this all the outputs described in detail, and we maybe will look into this in more detail tomorrow, but it's something I don't go through these tables now. It doesn't make much sense. But problem is sometimes really what's the definition of path scattered radiance, for instance. So it's because it has changed between MODTRAN 5 and MODTRAN 6, and so path scattered radiance in MODTRAN 6 is the one which is multiple scattered, path scattered, and the single scattered is only the the single scatter. So it's so one has really to read through these tables to see what's really in the outputs. Okay, so much for these two presentations of today. Questions about MODTRAN principles and MODO principles?
I remember other than the standard atmospheric profile, you can also key in your user if you have radiation data or the sounding atmospheric sounding profile. You can key in the real-time data instead of using the standard profile. I guess this is the thing it allow. I think the MODTRAN allow to get more representative of the atmospheric condition during your measurement or during the simulation. I think. But I think it probably doesn't matter much based on what you described earlier. If we had instead of using a standard, for example, standard tropical atmosphere, and you provide some real-time radiation data measurement, I don't think it differs much. Maybe based on your experience.
So our experience, yes, is indeed that using a radio sound profile doesn't help a lot in remote sensing. That's was our experience. The main reason is the radio sound profiles usually haven't been taken at the same location as your image is, and they are not taken at the same time. So it's very seldom that you really get a radio sound profile exactly at the time of overflight, which is valid for the simulation. So that's one major problem we are having there. And the other thing, we also you try to use radio sound profiles once, but it's quite some time ago, but for validation, and we saw that we just couldn't get better results. So we finally didn't know if the problem was the radio sound profile or if it was the simulation. So we I would say it would be an interesting exercise to try once more, but I wouldn't say that necessarily you get better results using radio sounds. About the use of radio sounds, I must say that I don't have a recent experience with MODTRAN using radio sounds. We only did this with MODTRAN 5 or even 4 some time ago, and so I would need to go into the atmospheric the HET toolkit. I think you have it, and there it says exactly how to format the radio sounds and then how to feed it to MODTRAN. So it's you have to create some ASCII file with the radio sounds according to their formats, and I think that's you can feed it. But I never did this in the last years. It must be about 10 years ago as I looked the last time into it.
Right. Thanks for the explanation. Thanks.
Any other questions regarding generic use of MODTRAN? Maybe I can get rid of this one. I can. It's a little bit too. I don't know if it's too small to read to see if I'm showing this interface like that. Some code to put away. Can you read that on the screen?
The font is rather small. The font is rather small.
Too small. Yeah. Maybe I'm gonna change the resolution of the screen. Just a moment. But oh well. It's just to give you how it should look like if it's once running on your system. Well, here it's on Linux like the appearance, but on Windows it will look more or less the same. It's my displays. Here it is. Just really doing it very large. Okay, now it should be. Is it better now?
Actually, I don't see the difference. Yeah.
I'm just trying to share it again. Where was it? It was here. Now it should be.
Yeah,
now
better.
It's better now.
Yeah.
Just how for the installation, a few words, because the goal is to install it on your machines, and if once licensed, it should look like that. If you look into the installation itself, you got the RISI software, Win, and so on, and then you receive a license key, a license key file, and this has to be put into the bin file. If you help about the license, you get something like this, such an alert window, where you have all the information, and there is we need the MAC ID of the machine to be licensed, and this one is coded into a file named risilicense.pro, which is to be put into the bin of the installation. So if you start it in unlicensed mode, you will get pop-up windows, and the third one will show you this dialog. And then we will have to create this license key and can send it over for each machine. This license key is valid for one machine, and it should be a physical machine and not a virtual machine, because virtual machines change the MAC ID with each startup, so you cannot use it easily. That's the first step of installation. The second step of installation is the MODTRAN licensing itself. So you find it in the help menu, MODTRAN licensing. So it's this dialog, and I already sent you a license key for your installation. So everybody has the same MODTRAN key in the group. It's a group license, and here you can activate the machine, and you can also deactivate the machine through just entering the code I sent you. So that's to run MODTRAN in the background. This second code is required. That's the code from Speckle Sciences. Make sure if you change the machine to deactivate the old machine and activate the new one. So there, for this one, we got a deactivation option. That's for MODTRAN licensing itself. Then for the installation, we have the install components in the help menu. So if you once are here, such that it starts like this, you have MODTRAN licensing and you have install components. And the install components looks like that. And for legal reasons, the base installation of MODTRAN is protected by a code. I put the code in the chat of the meeting today in the beginning. So you can install. I could also reinstall. Then you have to enter the download code, and then it will install the base installation of MODTRAN. So that's MODTRAN itself. So at first you don't have MODTRAN installed, you only have MODO. And if this is installed, what you need to run the software is the standard HYTRAN 2013. So that's the second last of the list. This 300 megabytes. So this needs to be installed in any case. The others are optional. So like the high resolution, that's 6 gigabytes, and that's something you don't need for multispectral. You need, if you want to have really fluorescence analysis at below 1 nanometer resolution, then you need the high resolution database. That's the same here. The test data you can download to do your own tests, and that's for the NOAA generation toolkit for radiosonde profiles can be installed. I'm not using this normally, but that's just how to download it. You can always check the connection. I'm getting a failure currently. That's on my side, but I don't know why. That's strange. Because it's restricted. So it's connecting to the. We need the code. So in your case, it worked before I installed that one, and on the machine you provided this morning, and you can try to install yourself now. And if once it's installed, you should be able to set up JSON. I'm just loading one, and you can run MODTRAN on that. And so this is just a standard one which has been loaded, and you can have a short look at the outputs by MODTRAN plot tape 7 output. So that's by default, it takes the one which has just been created, and then you get this kind of outputs you have seen before in the lecture as a first view of what has been created as an output. So this is just to give you a first overview of what can be done, how to install and how to check it. And so at least to this point, you should be able to get